So there's a relationship between temperature change and heat that is transferred. When a system absorbs heat, its temperature increases. And again, we use that delta symbol. This is a Greek letter delta. I know it looks like a triangle. It is a triangle, but it's also a delta, meaning change in. Delta T is the final temperature minus the initial temperature. If the temperature goes up, delta T is positive. If the temperature goes down, delta T is negative. The increase in the temperature is directly proportional to the amount of heat. You put in more heat, the temperature change is greater. You put in less heat, the temperature change is less. And so we have a proportionality constant. The Q is the energy that is put into the system is proportional to the change in temperature, or vice versa. C is a proportionality constant. We call it the heat capacity. And the units are typically expressed either in joules per degree Celsius or joules per Kelvin. Because Q is going to be in energy units of joules, and the change in temperature could be degrees Celsius or Kelvin, doesn't matter. And so in order for the units to work out, the heat capacity has units of energy per temperature unit. So the heat capacity is the heat required to change the temperature of the system by 1 degree Celsius. It's joules per degree Celsius. And that heat capacity is going to be different for different substances. If you have an object with a large heat capacity and you put heat into it, its temperature will only change a small amount. If you have something with a low heat capacity and you put energy into it, the temperature will change by a larger amount. The heat capacity depends on the amount of matter, which is usually measured by mass. If you think about boiling water. So if you have a little tiny saucepan and you put it on the stove and you turn it on full blast and you've got 1 cup of cold water, and you also have a big Dutch oven with like 8 quarts of water, and you put that on a matching burner and you crank that up as high as you can as well. You're putting the same amount of energy into each pot, but one of them is going to change its temperature much faster, isn't it? The amount of energy to heat the large quantity of water is greater than the small quantity of water. I think that makes intuitive sense. So the heat capacity depends on the size of the object. That makes heat capacity an extensive property. Intensive properties do not depend on the size of the object. Extensive properties do. Well, because heat capacity is extensive, depending on the size of the object, that makes it not all that useful, because we have to always be considering the size of the object. So what we do is we have what's called the specific heat capacity. The heat capacity of the object also depends on what that substance is made out of, what that object is made out of. The specific heat capacity is an intrinsic quantity. It's the intrinsic capacity of a substance to absorb heat. And so specific heat capacity is what we're going to use because it does not depend on the size of the object. So specific heat capacity is the heat needed to raise the temperature of 1 gram of the substance by 1 degree Celsius. And so this is going to have units of joules per gram degree Celsius, whereas the heat capacity was just joules per degree Celsius. So that's specific heat capacity. Molar heat capacity is related, but instead of 1 gram, it's the heat needed to raise the temperature of 1 mole of substance. And so then the units are going to be joules per mole degree Celsius. Both of these are intensive properties. They've got the size of the object kind of figured into the quantity. And this is where an understanding of dimensional analysis and how to mess around with units is really helpful. Because you see a number with units like this, and you want to find the heat needed, well, you know that you need to multiply by number of moles and multiply by degrees Celsius. The units will actually help you out a great deal in telling you what you should multiply by. So when we quantify this, so here's the heat, Q. So the heat is going to be the mass of the object times the specific heat capacity times the change in temperature. The specific heat capacity is something that you would be given or you would look up in a table. Here's a nice little table for us. Here's some elements and their specific heat capacities. The units are always given in the table, joules per gram degrees Celsius. Here's a couple of compounds and some other materials, like Pyrex glass and graphite and sand. So we can do examples. Hang on just a minute here. So let's do this example. A 55 kilogram, where did that come from? 55.0 gram aluminum block, initially at 27.5 degrees Celsius, absorbs 725 joules of heat. What is the final temperature of the aluminum? Well, we're going to use this equation. Q equals mc delta T. It kind of looks like MCAT, if that helps you to remember it. Q equals mc delta T. The delta kind of looks like an A. Well, Q equals MCAT. Well, we're looking for a temperature. Well, the temperature is hidden in this delta T, the final temperature. Let's remember that delta T is T final minus T initial. So there are easier ways and harder ways to do this. We're going to do it the easier way. So we're trying to find the final temperature. We're given the initial temperature. So what we should do is solve this equation for delta T, and then we can figure out what the final temperature is from this equation over here. We can do that with less algebra than combining it all together. So I'm going to take that MCAT equation and just rearrange it, and that will give us delta T is equal to Q divided by the mass divided by the specific heat capacity. So now we need to know what Q is. Q is heat. Q is heat. Heat is a form of energy, so that's 725 joules. Include the units. It's really important. The mass. We need the mass. Well, that's given to us too. 55.0 grams. We need the specific heat capacity. When you're doing homework problems, you may have to go into the book and look for it. It's in table 6.4 in your textbook. So we look on there, we find aluminum. Specific heat capacity is 0.903. Write down the units. Joules per gram degrees Celsius. And then we will look at that and make sure that our units are okay, because they'll try to trick you, won't they? They'll put one of these in calories, or they'll give you this in pounds or something crazy and make you convert units before you can actually use the equation. That's why you always want to put the units in and make sure that everything's going to work out okay. And here we're fine. Joules are going to cancel out, grams are going to cancel out, and we're going to end up with degrees Celsius, which is what we want. And I forgot to get out my calculator, so we'll use the cell phone. 725 divided by 55. Now here we've got two numbers in the denominator, so be careful. Divided by 0.903. And how many sig figs should this have?
3.
Should have 3. So delta T is going to equal 14.5978. That's 3 significant figures. I'm carrying along some extras. That's not our final answer, though, is it? That gives us the change in temperature. Here's our initial temperature. Delta T is the final minus the initial. So if we want to rearrange this and solve for final temperature, we're going to add the initial temperature on this side. So those will go to 0, and we'll add initial over here. So we end up with the final temperature. T final is equal to the initial temperature. Okay, I'm just like, the initial temperature plus the change in temperature. So the initial temperature was 27.5. The change was 14.5. Wow. 5978. If I didn't do that all the time, I'd really be concerned about myself, but there seems to be some short circuit in my brain sometimes. That's a 7 and that's a 2. They kind of look alike. 27.5. Try that again. Plus 14.5978. So there was uncertainty in the tenths place of our change in temperature. Our initial temperature has uncertainty in the tenths place. So we're going to report our answer, I'll put it over here, is 42.1 degrees Celsius. So 55-gram aluminum block starting at 27.5 degrees Celsius. It absorbs 725 joules of heat, ends up at 42.1 degrees Celsius. Any questions? My question is, why can Evernote not just leave me alone? Bless you. Water actually has a high specific heat capacity. It can absorb a lot of heat before it changes temperature. And this is pretty significant in terms of climate and many other things. I think we recognize, especially living here in the Central Valley of California, which is very desert-like at times, that our weather here, we have much more extremes of temperature than they do at the coast. We lived in the Bay Area for a while, and the average temperature between winter and summer didn't change much. It was like maybe 5 degrees. It was really kind of crazy. Why is that? Well, San Francisco is surrounded by water. Water has a very high specific heat capacity, meaning the sun beats down on it, sending energy into the water. It takes a lot of energy to warm up the water. And then at night, all the energy that went into that water then is released as the air cools down. The heat flows the other way from the water to the air, but it can give off a lot of energy. And so it acts as this stabilizing force, and it keeps the temperature from fluctuating much. Here, we can get a 40-degree temperature change in a day, right? It could be 60 at night, and it could easily be 100 in the afternoon, because there's very little water around here. We don't have much water in the air. There's no large bodies of water. hanging around to work as heat sinks and heat sources. We often use water as a coolant because it can absorb a lot of heat, like in your engine. Most of your radiator fluid is water. It can absorb a lot of heat from the engine without changing its temperature as much as many other substances. So when we have two objects at different temperatures, the heat flows from the high temperature to the low temperature until they reach the same temperature. And the amount of heat lost by the hot one is equal to the amount of heat gained by the cold one. The heat energy lost by one is gained by the other. So we can do things that take advantage of this. Temperature change is something we can measure. It's hard to measure a flow of energy, but we can measure the result of that, which is a temperature change. So if we take a block of metal at 55 degrees and put it in water at 25 degrees, what's going to happen? The metal is going to give thermal energy to the water. The metal's going to cool down. The water's going to heat up. So there's going to be a flow of energy until it gets to the same temperature. And the exact temperature change is going to depend on a couple of different things. It's going to depend on the mass of the metal and on the mass of the water. So what we have is that the heat Q of the metal, the heat that's lost by the metal, is going to equal the heat gained by the water. Whether you put the negative sign on this side or that side doesn't matter. It's just that one gains, one loses. And the heat is equal but opposite in sign. Another way to think of it is that the heat of the water plus the heat of the metal has to equal 0. So Q metal plus Q water equals 0. Which side that negative ends up on just depends on how you rearrange this equation. Well, what's Q for the metal? It's MCAT, right? Oops. How did I do that? I hate it when that happens. I don't know. That's not coming back. It's fine. Q metal is MCAT. The mass of the metal, the specific heat capacity of the metal, the temperature change of the metal. That's going to equal the mass of the water, the specific heat capacity of the water, and the change in temperature of the water, but the sign's going to be opposite. The sign's going to be opposite because one of these has a positive delta T and one has a negative delta T. So let's do an example. Block of copper of unknown mass has an initial temperature of 65.4 degrees Celsius. The copper is immersed in a beaker containing 95.7 grams of water at 22.7 degrees Celsius. When the two substances reach equilibrium, the final temperature is 24.2 degrees Celsius. What is the mass of the copper block? Well, we're going to need the specific heat capacity of copper. So I'm going to go back to that table before I start writing anything. Copper is 0.385. So write that. Write that on the board so I don't forget. So we're using this one, what am I pointing at? Copper, 0.385 joules per gram degree Celsius. We're also going to need the specific heat capacity of water. Do you notice how much higher that is? 4. Copper is less than 1 and water is over 4. So that's a big difference. So here we go. So let's draw a picture. So we have a beaker. Yeah. We have a beaker. Okay, and it's got water in it. And we know the mass of the water is 95.7 grams. And the initial temperature of the water is 22.7 degrees Celsius. And then there's this copper block that's put into there. That has an initial temperature of 65.4 degrees Celsius, and we don't know what the mass is. So that's the mass of the water. The mass, we don't know. Now, this is not the simplest way to find the mass of a block of copper. I would recommend using a balance, but that wouldn't demonstrate this problem, would it? What is the final temperature for the water? 24.2. What's the final temperature for the block of copper? Same thing. They come to the same temperature. We're going to do a fair number of problems like this. And you could learn the equation and how to plug numbers in, and you might be successful doing that. I think a much better strategy is to be able to think about what's happening. So we've got this block of copper metal. It's hot, 65 degrees. We put it in this beaker of cold water at 22.7 degrees. The block cools down, the water heats up until they get to the same temperature. The final temperature is the same for both. Okay? Don't forget to turn your common sense on. So the final temperature is the same for both. And then what we know is that the heat lost by the copper must be gained by the water. We are going to assume, for purposes of simplicity, that there's no loss from the beaker to the outside. There probably is, but we're going to ignore that. So we know that Q for the metal plus Q for the water is equal to 0. And for both of these Q's, Q equals MCAT, the mass times the specific heat capacity times the change in temperature. Well, what are we trying to find out? We're trying to find out the mass of the copper. So we're looking for this for the copper. So here is Q for the metal. That has the mass in it. So let's leave this on the left side and move QW to the right side. So QM equals negative QW. Now let's substitute in what the Q's are. So Q for the metal is the mass of the metal times the specific heat capacity of the metal times the change in temperature for the metal. Q equals MCAT. So here, instead of writing Q, I'm going to write MCAT. And that equals negative mass of the water, specific heat capacity of the water, change in temperature of the water. You follow what I'm doing? The total change of energy in the universe is 0. Right? So these have to add up to 0. The heat lost by the metal has to be gained by the water. I'm just rearranging these. I'm subtracting QW from both sides to get QM. Q of the metal is equal to negative QW. The Q's are equal in size, magnitude, but they're opposite in sign. I gain $5, that means you lose $5. One of us is plus 5, one of us is minus 5. What does QM equal? Well, QM equals MC delta T for the metal. So that's the mass of the metal, specific heat capacity of the metal, and the change in temperature of the metal. What is QW? It's the mass of the water, specific heat capacity of the water, delta T for the water. That's where I'm getting this. What are we trying to find? We're trying to find the mass of the metal. So we can rearrange this equation. I know it gets a little weird looking with all these subscripts, but we have more than one M and more than one T, and so we have to keep track of what they are. So I'm going to rearrange this. I'm going to divide by, I'll do it on this side first. I'm going to divide by the specific heat capacity of the metal and the change in temperature of the metal. Because I want those guys to go away, get to the other side of the equal sign. If I do that to one side, I have to do that to the other side. So now I have an equation that's giving me the mass of the metal. All I had to memorize to get this equation is knowing that the sum total of these energy transfers has to be 0 and that Q is MCAT. And then I think about it and I put it together and I rearrange things. Well, we haven't found out what delta T is. Let me get rid of that. Delta T for the water is the final minus the initial. So we've got final and initial. We can calculate that. It's the final, 24.2, minus the initial. I don't want to do that in my head. 24.2 minus 22.7, 1.5. Okay, we need more space. Yeah, that black smudge up there, that's actually on the wall. It's not on the screen. It's bothering me. Okay. We need delta T for the metal. So delta T for the metal is also the final minus the initial. The final is the same, 24.2 degrees Celsius. The initial is 65.4 degrees Celsius. 24.2 minus 65.4, negative 41.2. One of the temperatures is positive and one is negative, delta T, because one's going up and the other's going down. They have to be opposite in sign. If you don't end up with a negative delta T somewhere, then you're doing something wrong. So we can take these numbers now and plug them into the equation there on the bottom. I'm going to write it on the top because I think I need more room. So the mass of the metal is equal to negative the mass of the water, 95.7 grams, times the specific heat capacity of water, which we looked up before and wrote on the whiteboard, was 4.18 joules per gram degrees Celsius, times the change in temperature for the water, 1.5 degrees Celsius. That is divided by the specific heat capacity for the copper block, which is 0.385 joules per gram degrees Celsius, and the change in temperature is minus 41.2 degrees Celsius. We've got this guy, and this guy, and this guy, and that guy, and then the two specific heat capacities that we looked up in the table. Those didn't come out of nowhere. We looked them up. So now we do math. 95.7 times 4.18 times 1.5 divided by 0.385 divided by negative 41.2 equals, and then I have that minus sign, so I'm going to change the sign on the whole thing. And it looks like I should have how many sig figs? Close. This guy, 2. So that 37.8287101 is going to round to 38 grams. Any questions? If what?
The change in temperature of water both started with 36 things. Should the 1.5 happen 0?
That's a good question. If our final and initial temperatures for the water each had 3 significant figures, how can this only have 2? It's because we were subtracting. Yeah. So we've got rules for subtracting, and we've got rules for multiplying and dividing, and this is why we made a deal out of this at the beginning. It's because it comes into things like this. Any other questions? A problem like this, if you can't keep the big picture of what you're doing and you can't write your work out clearly, can quickly become just like a tar pit or something that you drag down into and you're stuck, right? So you have to be able to get at least a mental picture of what's going on. And even those of you who are really good at doing stuff in your head, I really encourage you to write some of this down. Okay, I think at the very minimum, you should write down your rearranged equation, and you'll write down these change in temperatures before you plug them in, and then always, always, always include your units in there. How do those units work out? Let's look at that real quick. Well, here gram cancels gram. And degrees Celsius cancels degrees Celsius. And down here, degrees Celsius cancels degrees Celsius. And that joule cancels this joule. The units end up 1 over gram, which is grams. There are different kinds of work. One of them is called pressure-volume work. And this is work caused by a volume that's changing against an external pressure. So a gas expanding against pressure. So the gas expands, delta V is positive, but the system is actually doing work on the surroundings, so the work for the gas is negative. We've got the gas in here, and it's pushing up on the piston. It is doing work on the surroundings. And so the overall work from the point of view of the gas is negative. So here W is negative the pressure times the volume change. Now the pressure is not negative, the change in volume is not negative. But we put this minus sign here because the gas is doing work on the surroundings. And when you do work on something else, that's an outgo for you. That's a negative thing for you. It's not someone doing something on or for you. It's you doing something for someone else. So the work is negative P delta V. We end up with some weird units here. We can end up with atmospheres and liters. And how do we change that to energy? Well, 1 joule is equivalent to 1 atmosphere liter. I'm sorry, not 1 joule. 101.3 joules is 1 atmosphere liter. And so that's how we take care of the units. And that's really physics there, and you probably don't want to go there. I don't. Okay, so let's do an example. Cylinder equipped with a piston expands against an external pressure of 1.58 atmospheres. If the initial volume is 0.485 liters and the final volume is 1.245 liters, how much work in joules is done? So let's refresh our memory. 101.3 joules, let's write that down. 101.3 joules was equal to 1 atmosphere liter. This is pressure volume work, so we need that equation. W is minus P delta V. It's the pressure times the change in volume. Well, what's the change in volume? Delta is always final minus initial. What's the final volume? 1.245. What's the initial volume? 0.485 liters. $1.245. You know, it's good to keep your mind sharp and do subtraction like this in your head or something, but it's also good to get the right answer. And it's amazing how many times, especially on labs, I see people and they get their subtraction wrong, and then the whole answer's wrong. So go ahead and do it in your head, but check it on your calculator. This is a subtraction. This has 3 decimal places. This has 3 decimal places. My answer should have 3 decimal places. My calculator didn't know that. So I put that 0 in there because that is a significant figure. There's uncertainty in it, but we need to keep that. So that's the change in volume. So now we've got negative. The pressure is 1.58 atmospheres. The change in volume is 0.760 liters. And then it's asking for the answer in joules, so we need to use our little conversion factor here. So we're going to multiply by 101.3 joules per liter atmosphere, or atmosphere liter. So 1.58 times 0.76 times 101.3 equals, and I have to change the sign because of that negative. And how many sig figs should I have? 3. So this is going to be minus 122 joules. The sign is negative because the gas did work on the surroundings. Pressure volume work is the work that the gasoline does in your engine. When it explodes, it pushes the piston up, and it works against a pressure to do that. And so it is doing work on your engine. Any questions?